Out there, beyond the thin blue line of our atmosphere, lies a universe that doesn't just defy our expectations, it laughs at them. Think about it. We've sent robots to Mars that sing happy birthday to themselves, discovered planets where it rains molten glass, and found galaxies that spin like cosmic whirlpools. Space isn't just vast, it's downright bizarre, and every time we think we've got it figured out, it throws another curveball that leaves scientists scratching their heads. That's the magic of space exploration. It's a never-ending series of "wait, that can't be real, can it?" moments, and today we're diving into 30 of the weirdest, most wonderful facts that prove the universe is stranger than any sci-fi movie. Picture this, a star so dense that a single teaspoon of it would weigh as much as a mountain, or a black hole where time itself slows to a crawl, warping the very fabric of reality around it. These aren't plot twists from a fantasy novel, they're real, documented phenomena, the kind that make you pause and wonder how much we still don't know. And that's the thrill of it all. Every rocket launch, every distant probe, every flicker of light from the edge of the observable cosmos is a reminder that we're just beginning to scratch the surface. The more we explore, the more we realize how delightfully odd the universe truly is. So buckle up, because this journey is going to be anything but ordinary. We're about to uncover cosmic mysteries that sound too wild to be true, from astronauts growing taller in space to a planet where diamonds rain from the sky. These aren't just fun facts, they're glimpses into a reality far grander and more peculiar than we could have imagined. And by the time we're done, you'll see the night sky not just as a blanket of stars, but as a treasure chest of unanswered questions and mind-bending wonders waiting to be explored. Ready to have your sense of wonder cranked up to 11? Let's go! Here's something that sounds like a sci-fi superpower but is actually a quirk of human biology in space. Astronauts come back taller. That's right, spending time in microgravity can stretch you out by up to 2 inches. It happens because the lack of gravity allows the fluid-filled discs between your vertebrae to expand, like decompressing a spring. For astronauts, it's a temporary change, but imagine floating around the International Space Station and suddenly needing longer pants. Of course, this cosmic growth spurt isn't all fun and games. When astronauts return to Earth, their spines compress back to normal, often causing intense back pain as their bodies readjust to gravity's pull. That's why you'll see them moving cautiously after landing. Their muscles and bones have to relearn how to support their weight. NASA even had to redesign spacecraft seats to accommodate this height shift, making them adjustable so astronauts don't end up cramped on the ride home. This bizarre side effect of space travel reveals just how finely tuned our bodies are to Earth's gravity. Every inch of us, from our bones to our circulation, depends on that constant pull. Take it away and things start to stretch, literally. It's a humbling reminder that even the most ordinary parts of being human can turn extraordinary when you leave the planet behind. The moon has a secret it's been hiding for billions of years, a scent that caught Apollo astronauts completely off guard. After clambering back into their lunar modules, peeling off their helmets, and taking that first deep breath, they were hit with something unexpected: the sharp, acrid smell of burnt gunpowder. Lunar dust, fine as powdered glass and clingier than static-charged socks, had coated their suits, and with it came this bizarre metallic tang that lingered like campfire smoke on clothes. Scientists have a few theories about why the moon smells like a spent shotgun shell. One leading idea points to the dust's composition, packed with tiny shards of silicate minerals, all oxidized and fractured by eons of meteorite impacts and solar radiation. In the vacuum of space, those broken edges stay chemically fresh, like a just-cracked geode. But when astronauts brought them into the pressurized cabin, those minerals finally reacted with moisture and oxygen, unleashing that pungent aroma. It's like uncorking a bottle of cosmic wine that's been aging in absolute zero. What's even weirder, the dust didn't just smell strange, it behaved like nothing on Earth. Without weathering or erosion to smooth its edges, lunar regolith is viciously abrasive. It clogged suit joints, scratched helmet visors, and even seeped into the seams of sample containers. Some astronauts compared it to handling crushed diamonds, and that gunpowder scent, it haunted their gear for days, a ghostly reminder of their walk on a world where even the dirt plays by different rules. This quirky lunar quirk isn't just a fun fact, it's a cautionary tale for future missions. Moon dust isn't just dirt, it's a chemically hyperactive relic of the solar system's violent past, and we'll need to outsmart it if we're ever going to live there. Imagine building a moon base only to have its air filters clogged with scented, razor-sharp powder. The moon, it turns out, doesn't just look extraterrestrial, it smells like it too. If you think traffic on Earth moves the wrong way, wait until you hear about Venus, the solar system's ultimate rebel. While most planets spin counter-clockwise like graceful ballerinas, Venus does a full cosmic pirouette in reverse, rotating clockwise in what scientists call a retrograde motion. But that's not even the weirdest part. A single day on Venus lasts longer than its entire year. That's right, the planet takes 243 Earth days to complete one rotation, but only 225 Earth days to orbit the Sun. Imagine celebrating your birthday before you've even finished one full day-night cycle. So why does Venus break all the rules? One leading theory suggests a colossal collision billions of years ago. A planetary smash-up so violent it sent Venus spinning backward like a billiard ball struck just wrong. Another idea points to its thick, churning atmosphere, a suffocating blanket of carbon dioxide and sulfuric acid clouds. The drag from these supercharged winds might have gradually slowed and reversed the planet's spin over eons, like a brake applied to a runaway tire. This backward dance has terrifying consequences. Venus's sluggish rotation means each side bakes under the sun's fury for months, contributing to surface temperatures hot enough to melt lead. Those sulfuric acid clouds, they're not just toxic, they whip around the planet at hurricane speeds, fueling perpetual storms in a sky that never truly darkens. Even the sun rises in the west and sets in the east, as if the universe flipped a switch on reality itself. Yet Venus isn't entirely alone in its defiance. Uranus also spins on its side, likely from a similar ancient cataclysm. But Venus takes the crown for sheer audacity, a world where time and motion obey no earthly logic. It's a reminder that even in the orderly clockwork of the solar system, there's always room for a renegade. Here's a cosmic paradox that'll bend your ears. Space is utterly silent, yet filled with eerie noises. In the vacuum between stars, sound waves, those vibrations that normally travel through air or water, have nothing to push against. It's like an infinite, airless concert hall where no note can ever play. But that doesn't mean space is mute. With the right tools, scientists have turned the vibrations of planets, stars, and even spacecraft into spine-tingling sounds that reveal secrets no telescope could capture. Take Cassini's haunting recordings of Saturn. As the probe orbited the ringed giant, it detected radio emissions from the planet's magnetosphere, a symphony of charged particles dancing along magnetic fields. When scientists converted those signals into audible frequencies, the result was downright otherworldly, crackling static, ghostly whistles, and pulses that sound like a theremin played in a horror movie. These weren't sounds in the traditional sense, but they painted an acoustic portrait of Saturn's invisible forces, as if the planet itself was whispering its secrets in Morse code. Then there's the Sun. NASA's Solar Dynamics Observatory captured vibrations from solar flares and coronal loops, translating them into deep, resonant hums that resemble Tibetan singing bowls. Each note corresponds to magnetic loops writhing in the sun's plasma, a reminder that our star isn't just a ball of fire, it's a colossal, vibrating engine. Even black holes get in on the act. In 2022, astronomers sonified the pressure waves rippling through the Perseus galaxy cluster, amplifying them 57 octaves to reveal a basso profundo drone, like the universe's deepest cello note played over 1 billion years. But perhaps the creepiest space sounds come from our own backyard. The Apollo missions left seismometers on the moon, and when meteorites struck the surface, they triggered moonquakes that rang out like a giant hollow bell. Lunar seismic waves take minutes to fade compared to seconds on Earth because the moon's dry, fractured crust vibrates like a shattered wine glass. It's a reminder that silence isn't the absence of noise, but a canvas for the universe's strangest frequencies. So next time you gaze at the stars, remember, the cosmos might not speak our language, but it's always broadcasting. All we have to do is listen through the static, the hums, and the echoes to hear the music of the spheres. Saturn doesn't just have rings, it's hiding a colossal, razor-edged hexagon at its north pole, a storm so precise it looks like it was etched by cosmic architects. This six-sided monster is 20,000 miles wide, big enough to swallow 2 Earths side by side, and it's been spinning there for at least 40 years, possibly centuries. Unlike the swirling chaos of Jupiter's Great Red Spot, Saturn's hexagon is a geometric marvel, its angles so sharp they defy everything we know about planetary weather. It's as if the universe took a protractor to the gas giant and said, "Let's break the rules." So how does a planet produce a storm with corners? Scientists suspect it's all about jet streams, rivers of wind roaring at 320 miles per hour colliding with Saturn's layered atmosphere. On Earth, jet streams meander like drunken snakes, but Saturn's rapid rotation and lack of solid land might force them into this rigid polygon. Picture a spinning top. The faster it goes, the more stable its shape becomes. Now imagine that top is the size of a planet, and you've got a clue why this hexagon locks into place like a celestial honeycomb. But the real magic happens inside the hexagon. Infrared images reveal a towering wall of clouds stacked 60 miles high, where winds shear against each other like gears in a cosmic clock. At its center, a churning vortex acts like the eye of a hurricane, but instead of chaos, it's surrounded by that eerie symmetry. Some researchers compare it to laboratory experiments where swirling fluids spontaneously form polygons, except Saturn's version is scaled up to planetary proportions, a natural experiment we'd never dare try on Earth. What's even stranger, the hexagon changes color with Saturn's seasons. As winter gripped the North Pole in 2012, the storm shifted from a deep blue to a golden haze, likely as sunlight sparked chemical reactions in its upper atmosphere. It's a reminder that this isn't just a static shape, it's a living, breathing weather system, one that operates on scales and time spans we can barely fathom. This isn't just a curiosity, it's a masterpiece of fluid dynamics. The hexagon challenges our assumptions about how atmospheres behave, proving that even in the infinite variety of space, nature has a flair for the geometrically dramatic. So next time you see Saturn's rings, remember, hidden in the shadows of its North Pole, there's a storm that plays by its own rules, one straight out of a cosmic kaleidoscope. We often picture the sun as a glowing beach ball in the sky, but the reality is so vast it redefines the word enormous. At its core, you could pack 1.3 million Earths side by side, like stuffing an entire planet's worth of rock, oceans, and atmosphere into a space no bigger than a marble, then repeating that 1 million times over. And this isn't just empty volume. Every cubic inch of that core is a nuclear furnace running at 15 million degrees Celsius, where atoms are smashed together with such force they fuse into new elements, unleashing the energy that lights our solar system. What's wild is that the sun isn't burning like a campfire at all. Fire needs oxygen, and there's none in space. Instead, the sun is a writhing ball of plasma, a fourth state of matter where electrons are ripped from atoms, creating a superheated soup of charged particles. This plasma doesn't just glow, it churns like a cosmic lava lamp with currents so powerful they generate magnetic fields capable of birthing sunspots the size of Jupiter. To grasp just how dominant the Sun is, consider this. It makes up 99.8% of the solar system's total mass. All the planets, moons, asteroids, and comets combined. They're barely a rounding error. Jupiter, the largest planet, is just 1,000th of the Sun's weight. Even if you lined up every rocky world, gas giant, and icy dwarf from Mercury to Pluto, they'd still be like a sprinkle of sand next to a bonfire. Yet for all its fury, the Sun's energy takes a slow, meandering path to reach us. Photons born in the core don't zip straight out, they're absorbed and re-emitted trillions of times in a drunken zigzag that can take tens of thousands of years just to reach the surface. Once they finally break free as sunlight, those particles still need 8 minutes to cross 93 million miles to Earth. That warmth on your face. It's the echo of a journey that began when woolly mammoths still roamed the planet. This isn't just scale for scale's sake. The Sun's mind-bending proportions are why life exists at all. Its gravity holds the solar system together, its light fuels photosynthesis, and its plasma storms shape Earth's auroras. But here's the humbling twist. In the grand scheme of stars, our Sun is utterly average. There are red dwarfs smaller than Jupiter and hypergiants that could swallow Saturn's orbit whole. The universe doesn't just do big, it does unthinkable. And our local star is just one note in a symphony of cosmic extremes. Jupiter's Great Red Spot has been the solar system's most iconic storm for at least 400 years, a swirling, crimson maelstrom big enough to swallow Earth whole. But something unsettling is happening to this ancient tempest. It's shrinking and fast. When astronomers first trained telescopes on Jupiter in the 1600s, the storm stretched 25,000 miles wide enough to fit 3 Earths side by side. Today, it's barely half that size, and recent measurements show it's narrowing faster than anyone predicted, like a cosmic balloon losing air. If this keeps up, the Great Red Spot might not be so great or even red for much longer. What's strangest isn't just the shrinking, but how it's happening. The storm isn't fading evenly, it's being sculpted, almost as if invisible hands are peeling it apart. High-resolution images from the Hubble Space Telescope reveal tendrils of ammonia-rich gas spiraling away from the spot like streamers in a hurricane, while smaller vortices gnaw at its edges like piranhas. Some scientists think these smaller storms are stealing its energy, breaking up the colossal circulation that's kept it spinning for centuries. Others suspect changes in Jupiter's jet streams. Rivers of wind that flow east and west are strangling the storm from within, like tightening a noose around a runaway engine. The real mystery: why now? This storm has survived solar cycles, comet impacts, and Jupiter's own chaotic weather for generations. Some theories point to a deeper shift in the planet's atmosphere, where rising temperatures or chemical changes might be sapping the storm's fuel. It's even possible the spot is a victim of its own success. Having chewed through so much of Jupiter's turbulent atmosphere, it's simply running out of chaos to feed on. If the Great Red Spot vanishes, it won't just be a loss for celestial postcards. This storm is a living laboratory, a window into how gas giants churn and evolve over millennia. Its winds, which scream at 430 miles per hour, are a textbook example of fluid dynamics at planetary scale. Without it, we'd have no way to study such a perfect, long-lived vortex unless, of course, another rises to take its place. And that's the wild card. Jupiter's atmosphere is a factory of monstrous storms. The Great Red Spot might be dying, but somewhere in those churning clouds, the next Titan could already be stirring. So keep an eye on Jupiter. The solar system's oldest weather system is teaching us its final lessons, and proving that even the mightiest storms are just temporary ripples in the universe's endless flux. Mercury, the scorched innermost planet, holds a secret that defies logic. Ice. Not just a few frosty patches, but vast deposits of water ice lurking in permanently shadowed craters at its poles, even as the sunlit surface bakes at 800 degrees Fahrenheit. How does ice survive on a world where daytime temperatures could melt lead? The answer lies in Mercury's unique dance with the sun. Unlike Earth, Mercury has almost no axial tilt, so its poles never lean toward sunlight. Deep craters there are forever cast in darkness, cold traps where temperatures plummet to -290 degrees Fahrenheit, colder than Pluto. These shadowy pits become cosmic freezers, preserving ice delivered by comet impacts over billions of years. But here's the twist: this ice isn't pure. Radar observations from Earth and NASA, a messenger probe, revealed it's mixed with dark organic material, like a dirty snowball stamped with the fingerprints of ancient comets. Scientists think these volatile compounds, water, carbon, and even methane, hitched rides on icy comets that smashed into Mercury, vaporizing on impact but then migrating to the poles where the cold trapped them like bugs in amber. It's a cosmic recycling program. The same comets that might have seeded Earth with water also stocked Mercury's deep freeze larder. What's even wilder? The Moon has the same phenomenon. Shackleton Crater near the lunar South Pole is a frosty vault, its floor shrouded in eternal night. Apollo astronauts suspected it, but it took India's Chandrayaan-1 orbiter to confirm it in 2008. Water ice hiding just feet below the dust. Both worlds, one blisteringly hot and the other airless and still, share this bizarre quirk: ice surviving in the unlikeliest places, thanks to shadows colder than the void between stars. This isn't just a curiosity, it's a game changer for exploration. Future moon bases could mine polar ice for drinking water and rocket fuel. Mercury's deposits, though harder to reach, are a time capsule of the solar system's volatile history. Imagine tapping into ice that predates dinosaurs, frozen before multicellular life existed on Earth. These shadowed craters are more than geological oddities. They're nature's way of proving that even in the harshest environments, the universe finds a way to stash its treasures. Pluto may be small, but it plays by its own extravagant rules, starting with a day so long you'd need a week's worth of coffee to see it through. While Earth spins like a top, completing a full rotation every 24 hours, Pluto drags out each day for 6.4 Earth days. Imagine waking up to a sunrise that takes over 3 days just to crest the horizon, with shadows crawling across the landscape at a snail's pace. This glacial spin isn't just a quirk, it's a side effect of Pluto's gravitational tango with its largest moon, Charon. The two are tidally locked, forever facing each other like dance partners in a slow-motion waltz across the void. But Pluto's slow days are just the opening act. Its axis is tilted a staggering 122 degrees, so extreme that the dwarf planet practically rolls around the sun like a ball on its side. For decades at a time, entire regions are bathed in perpetual sunlight or plunged into endless night. Seasons here aren't gentle transitions, they're cinematic extremes. When NASA New Horizons probe flew by in 2015, it caught Pluto's northern hemisphere in late spring, revealing a heart-shaped glacier named Tombaugh Regio, made of nitrogen ice as smooth as freshly poured frosting. This icy heart isn't just decorative, it's a dynamic engine, evaporating on the sunlit side and refreezing in the shadows, driving winds that sculpt Pluto's thin, hazy atmosphere. And what an atmosphere it is! New Horizons captured backlit images of Pluto's sky glowing an ethereal blue, layered with hydrocarbon haze that extends miles above the surface. Sunlight scattering through these particles creates a twilight worthy of a fantasy novel, painting the dwarf planet in dusky shades even at high noon. But don't let the beauty fool you, this sky is fragile. As Pluto retreats from the Sun on its eccentric orbit, the atmosphere will gradually freeze and snow back onto the surface, leaving it airless until the next close approach decades later. The real marvel, Pluto's sluggish rotation and wild tilt should make it a lifeless ice ball, yet New Horizons found a world shockingly alive. Towering mountains of water ice, hard as granite at these temperatures, rise beside glaciers of flowing nitrogen. Dunes of methane snow stretch across plains, and cellular patterns in the ice suggest heat bubbling up from below like a cosmic lava lamp. This isn't just a relic of the solar system, it's a geologically active underdog rewriting the rules for small planets. So while Pluto may have lost its planetary status, it's gained something far more compelling. The title of solar system's most unexpected drama queen, where days crawl, seasons last lifetimes, and the sky itself collapses and rebuilds like a celestial stage set. And somewhere in that slow-motion ballet of ice and haze, there's a lesson that even on the fringes, the universe never runs out of surprises. We're used to sunsets painting our skies in fiery reds and oranges, but step onto Mars and the rules flip entirely. There, the sun dips below the horizon in a haunting shade of blue. This isn't some artist's rendition. NASA's Perseverance rover has captured the phenomenon in stunning clarity, showing a twilight glow that looks more like Earth's deepest ocean than anything you'd see in a desert. The reason: Martian dust plays a cosmic game of pinball with sunlight, scattering blue wavelengths forward while letting red slip away. It's the exact opposite of what happens on Earth, where our thicker atmosphere scatters blue light during the day but lets red dominate at sunset. What makes Mars' blue hour so special isn't just its beauty, it's a window into the planet's atmosphere. The fine dust particles suspended in Mars' air are about 1/10 the width of a human hair, just the right size to bend blue light toward your eyes while the rest escapes. Perseverance's cameras have clocked these sunsets lasting up to 2 hours, with the blue glow intensifying as the sun disappears. Scientists call this Rayleigh scattering on steroids, a hypercharged version of the same physics that gives Earth its blue skies. But unlike our planet, where sunsets are fleeting, Mars' thin atmosphere stretches the show, turning twilight into a lingering performance. The real magic happens when you zoom in. Perseverance's images reveal a gradient of color, deep blue near the sun, fading to a dusky pink higher up. This isn't random, it's a fingerprint of the dust layers swirling through Mars' skies. By analyzing these hues, researchers can track dust storms, measure atmospheric pressure, even predict seasonal changes. It's like reading a weather report written in light. And here's the kicker: these sunsets aren't just pretty, they're survival tools for future astronauts. Mars' dust is so fine it clings to solar panels, and understanding how it moves could mean the difference between a powered habitat and a dark outpost. Those eerie blue twilights, they're more than a postcard moment, they're a roadmap to living on a world where the sky doesn't play by our rules. So next time you watch an earthly sunset, imagine standing on a rusty plain under a sapphire sky, where the sun doesn't set so much as it dissolves into a pool of liquid cobalt. That's Mars painting the cosmos in colors we're only beginning to decode. Neutron stars are the universe's ultimate speed demons, stellar corpses so dense they pack the mass of a sun into a city-sized sphere, spinning faster than a kitchen blender on its highest setting. Imagine a star that once stretched millions of miles across, collapsing down to just 12 miles wide after a catastrophic supernova. All that leftover energy doesn't just vanish, it gets funneled into mind-bending rotation, with some neutron stars whirling over 700 times every second. That's surface velocities approaching a quarter the speed of light, where a single misstep would fling you into orbit like a cosmic slingshot. The secret to this dizzying spin lies in a fundamental law of physics: conservation of angular momentum. Picture an ice skater pulling their arms in during a spin. Their body contracts and their rotation skyrockets, now scale that up to a dying star. When a massive star exhausts its fuel and implodes, its core compresses to a ludicrous density. One sugar cube-sized chunk would weigh as much as Mount Everest, and that shrinkage turbocharges its rotation. What was once a stately, days-long stellar spin becomes a millisecond frenzy, like a record player suddenly cranked to warp speed. But the real showstopper is what happens next. Many neutron stars become pulsars, cosmic lighthouses that sweep beams of radiation across space with metronomic precision. As the star's intense magnetic fields channel charged particles toward its poles, they emit focused jets of radio waves, X-rays, or gamma rays. If Earth happens to lie in the path of one of these beams, we detect rhythmic pulses, hence the name pulsar. The Crab Nebula's pulsar, for example, flashes 30 times a second, while others flicker hundreds or even thousands of times faster. These celestial strobe lights are so precise they rival atomic clocks, their pulses arriving with timing so predictable you could set your watch by them across interstellar distances. Yet even among these spinning marvels, some stand out. Take PSRJ 1748-2446 AD, the fastest known pulsar, rotating an astonishing 716 times per second. At that rate, its equator is moving at nearly a quarter the speed of light, so fast that if it spun any quicker, centrifugal force would rip it apart. That's the neutron star's ultimate limit, the point where gravity's grip can no longer hold it together against its own rotation. What's truly humbling is realizing these hyperactive remnants are everywhere. The Milky Way alone likely harbors hundreds of millions of neutron stars, some quiet, some pulsing, all bearing witness to the violent, beautiful chaos of stellar death. They're nature's way of reminding us that even in destruction, there's motion, a universe that never stops spinning, even when the lights go out. The Hubble Space Telescope's Pillars of Creation isn't just a stunning cosmic portrait, it's a time machine. Captured in 1995, this iconic snapshot of the Eagle Nebula's towering gas columns stretches 4 light-years tall, a celestial skyscraper where stars are born. But here's the twist, those billowing pillars glowing with ethereal beauty are already gone. Roughly 6,000 light-years away, the light Hubble captured left the nebula around the time humans first began writing. By now, a shockwave from a nearby supernova likely shredded these structures millennia ago, meaning we're staring at a ghost, a masterpiece of interstellar architecture frozen in light's slow crawl across space. What makes this image so revolutionary isn't just its haunting grandeur, it's the hidden story behind the dust. Hubble's original visible light photo showed the pillars as looming silhouettes, their surfaces illuminated by the radiation of young, searing stars nearby. But dust, thick as fog and just as opaque, blocked our view of the chaos inside. That changed in 2014 when Hubble revisited the scene with infrared vision. Suddenly, the pillars became translucent, revealing hundreds of newborn stars tucked within the gas like fireflies trapped in amber. Some were still swaddled in protoplanetary disks, while others had already burst free, their stellar winds carving cavities in the surrounding clouds like blowtorches through cotton candy. The real magic lies in the physics at play. Those pillars aren't passive sculptures, they're battlegrounds. Radiation from nearby massive stars constantly erodes them, a process called photoevaporation. Imagine sunlight hitting a snowbank, but instead of melting slowly, the surface boils away molecule by molecule. The densest knots of gas resist longest, sheltering pockets where gravity can pull material into new stars. It's a cosmic balancing act, destruction on the outside, creation on the inside. Hubble's infrared data exposed another surprise, tendrils of gas stretching behind the pillars like comet tails, invisible in the original image. These are the fingerprints of stellar winds, proof that the nebula is anything but static. The entire scene is a snapshot of chaos and order locked in a dance, where the same forces that tear down interstellar gas also sculpt the cradles for new solar systems. This isn't just art, it's a blueprint. Similar pillars likely existed in our own solar neighborhood billions of years ago, their collapsing gas giving rise to the sun and planets. When we study the Eagle Nebula, we're glimpsing our own origins, a factory floor where the universe forges stars, then scatters them like seeds across the galaxy. And thanks to Hubble, we've got a front row seat to the show. Up above our heads, hidden in plain sight, there's an invisible minefield moving 10 times faster than a bullet space junk. 500,000 pieces of debris, from defunct satellites the size of school buses to flecks of paint no bigger than a fingernail, are whipping around Earth at 17,500 miles per hour. At that speed, even a tiny screw becomes a lethal projectile, packing the kinetic energy of a hand grenade. The International Space Station regularly dodges these hypervelocity hazards, its hull peppered with dents from close calls we never hear about. And the scary part, every collision creates more debris, sparking a domino effect that could one day make entire orbits unusable. A nightmare scenario called Kessler syndrome. Imagine this: 2 dead satellites collide over Siberia, shattering into thousands of fragments. Those pieces then slam into other satellites, creating even more debris until low Earth orbit becomes a swirling storm of shrapnel. Suddenly, rocket launches become impossible without risk of instant destruction, GPS fails, and weather forecasts vanish. It's not sci-fi NASA. Scientists warned about this chain reaction back in the 1970s, and today, with over 8,000 tons of junk circling the planet, we're flirting with the tipping point. The European Space Agency estimates that a single collision between 2 large objects could double the debris risk overnight. So how do we clean up this mess? Engineers are getting creative. Some propose giant magnetic nets to snag derelict satellites, dragging them down to burn up in the atmosphere. Japan's JAXA tested a tether system that uses Earth's magnetic field to slow debris, while startups like Astroscale are developing robotic tow trucks to dock with dead satellites and to orbit them. Even lasers are on the table, zapping smaller bits to nudge them into decaying orbits. But the real challenge isn't just technology, it's politics. Space junk doesn't respect borders, and no single nation can solve this alone. Here's the irony: the same ingenuity that littered the skies might now save them. Scientists are tracking debris with radar networks, and new satellites are being designed to self-destruct or steer into graveyard orbits at mission's end. Meanwhile, the United Nations urges countries to follow guidelines for responsible space traffic. Though not everyone complies, the clock is ticking. Every year, near misses between satellites grow more frequent, and a single catastrophic collision could trap us on Earth like rats on a sinking ship. So next time you gaze at the stars, remember, the final frontier isn't just about exploration. It's about stewardship, keeping the highways of space clear so future generations can reach beyond our atmosphere without dodging the ghosts of our carelessness. The cosmos is vast, but our backyard is already a junkyard. Time to take out the trash. The moon may seem like a constant companion in our night sky, but it's actually inching away from us at a rate of 1.5 inches every year, about the same speed your fingernails grow. This slow-motion escape isn't just a curiosity, it's rewriting Earth's future in ways that would make a sci-fi writer jealous. The culprit: tides. Every time ocean waters bulge toward the moon's gravitational pull, that sloshing mass acts like a brake on Earth's rotation, transferring energy to the moon and nudging it into a higher orbit. Think of it like a figure skater extending their arms to slow down, except this dance has been playing out for 4.5 billion years, and the skaters are a planet and its celestial partner. Here's where it gets wild. This cosmic tug-of-war has measurable effects right now. Earth's days are getting longer, but not by much. A century from now, our descendants will have about 2 extra milliseconds of daylight thanks to the moon's retreat. Fast forward 1 billion years, though, and the story changes dramatically. By then, Earth's rotation will have slowed enough that a day lasts 25 hours, and the moon will hang noticeably smaller in the sky. The real finale comes in 50 billion years, when tidal forces finally lock the moon in synchronous rotation, much like how Pluto and Charon face each other eternally today. Earth and the Moon will be frozen in a gravitational embrace, one side of our planet perpetually moonlit while the other never sees its glow again. But this isn't just about distant futures. The Moon's getaway has left fingerprints all over Earth's history. Fossilized tidal patterns from 900 million years ago suggest days were only 18 hours long back then, with the Moon 15,000 miles closer. Coral growth rings from the Devonian period confirm that 400 million years ago, a year held 400 days, evidence of a faster spinning Earth before the Moon's drag took its toll. Even today, the precise laser reflectors Apollo astronauts left on the lunar surface let us measure the Moon's retreat down to the millimeter, turning our satellite into the ultimate laboratory for celestial mechanics. The irony: without the Moon's stabilizing influence, Earth would be a chaotic, wobbly mess. Mars, lacking a substantial moon, sees its axial tilt swing wildly over millennia, shifting climates violently between ice ages and tropical extremes. Our Moon's steady presence keeps Earth's tilt stabilized at 23.5 degrees, giving us predictable seasons. But as it drifts farther, that stability weakens. In the far future, Earth might start wobbling like a slowing top, turning climate into a roulette wheel. So next time you gaze at the Moon, remember, it's not just a pretty face in the sky. It's a timekeeper, a climate regulator, and yes, a runaway partner in a billion-year tango where every step leaves its mark. And while its slow departure won't trouble you or your great-grandchildren, it's proof that even the most familiar sights in the universe are part of an epic, ever-changing story. One where the tides don't just move oceans, they move worlds. If planets had personalities, Uranus would be the solar system's oddball recluse, the one that not only spins on its side but practically rolls around the sun like a drunken barrel. Clocking in with a 98-degree axial tilt, this ice giant doesn't just lean slightly off kilter like Earth's polite 23-degree slant. No, Uranus is fully committed to the bit, rotating perpendicular to its orbit path as if someone knocked it over billions of years ago and it just never got up. The leading theory for this cosmic quirk, a cataclysmic collision with an Earth-sized protoplanet early in the solar system's history, a smash-up so violent it sent Uranus spiraling onto its side like a top losing momentum. The aftermath is a world where seasons play out in brutal extremes. Picture this: for 42 Earth years, one pole basks in uninterrupted sunlight while the other languishes in frozen darkness. Then, as Uranus completes its 84-year orbit, the roles reverse. It's like flipping a cosmic switch between endless summer and unrelenting winter, with the equator getting fleeting glimpses of the sun in between. When Voyager 2 flew past in 1986, it revealed just how bizarre this sideways world truly is. Unlike Jupiter and Saturn, with their swirling storms and vibrant cloud bands, Uranus appeared as a featureless blue-green marble, its atmosphere shrouded in a uniform haze of methane ice crystals. Only later, with advanced telescopes, did scientists spot faint cloud streaks and a polar vortex hiding beneath that placid exterior. Even Uranus's magnetic field is eccentric offset from its center and tilted at a 60-degree angle, as though the planet couldn't resist adding another layer of weirdness to its resume. And then there's the name. Yes, it's pronounced Uranus, not the juvenile alternative, though astronomers have heard every joke. The moniker comes from the Greek sky god Ouronos, but honestly, chaos incarnate might have been more fitting. Uranus doesn't orbit the sun so much as it wobbles along like a wheel rolling downhill, its 13 rings and 27 moons caught in the gravitational crossfire. This isn't just planetary trivia, it's a lesson in cosmic violence. Uranus's tilt is a frozen snapshot of the solar system's chaotic youth, a reminder that even planets aren't immune to celestial collisions. And while its bland facade might seem boring at first glance, that icy calm is just a mask. Underneath, it's a world forever off balance, dancing to a rhythm no other planet understands. So next time you hear someone call Uranus the butt of the solar system, correct them. It's not the punchline, it's the enigma, the solar system's silent rebel, spinning sideways just because it can. Here's something nobody tells you about space travel when astronauts get emotional. They can't even cry properly. On Earth, gravity pulls tears down your cheeks in those dramatic streaks you see in movies. But in microgravity, tears have other plans. They pool into floating, quivering blobs that cling stubbornly to your eyeballs like stubborn jellyfish refusing to let go. Chris Hadfield, the Canadian astronaut famous for his Zero guitar covers on board the ISS, described it best. Your eyes might water, but the tears just form into giant bubbles that eventually float away if you shake your head too hard. Without gravity to drain them, those tear bubbles can linger uncomfortably long, sometimes stinging like salt water in a sunburn. NASA astronaut Andrew Fustel once had an allergic reaction in orbit, leaving his eyes red and irritated. But instead of dripping away, the tears formed thick, wobbly domes over his corneas, blurring his vision until he had to blink aggressively just to clear them. And forget tissues. In space, you can't exactly dab your eyes when tears decide to hover an inch from your face like tiny, personal rain clouds. The science behind this is both fascinating and slightly absurd. On Earth, tears rely on gravity to slide down your face, aided by surface tension and the natural curve of your eyelid. But in orbit, surface tension dominates, turning every teardrop into a self-contained sphere determined to stay put. It's not just crying, either even sweat clings to skin in eerie, expanding patches until it's shaken loose, and spilled drinks morph into floating liquid asteroids that crews have to chase down with absorbent towels. Astronauts train relentlessly for emergencies, but nobody prepares you for the weird intimacy of watching your own tears drift past your nose. Some compare it to wearing swim goggles filled with saline, while others say it feels like your emotions have literally escaped containment. And if you think rubbing your eyes helps think again, without gravity, that motion just smears the fluid around, making things worse, the only solution. Patience, a careful swipe with a finger which risks sending the tear sailing across the cabin, or waiting for the blob to evaporate. This quirk isn't just a quirky inconvenience, it's a reminder of how profoundly space rewrites the rules of being human. Even something as simple as shedding a tear becomes a strange, almost poetic act where sadness or joy literally floats in front of you, untouchable. Maybe that's the real lesson. In space, you can't hide your emotions. They just hang there, shimmering, until you figure out how to let them go. You'd think the coldest place in the universe would be some distant void between galaxies, or maybe the shadowy heart of a rogue planet drifting through interstellar space. But the truth is far stranger. The deepest cold humans have ever achieved exists right here on Earth, in laboratories smaller than your living room. Scientists have created Bose-Einstein condensates, exotic states of matter where atoms slow to a near standstill, at temperatures just a few billionths of a degree above absolute zero. That's colder than the Boomerang Nebula, the previous record holder, where natural temperatures plunged to -272 degrees Celsius, barely 1 degree above the theoretical floor of -273.15. Here's the wild part. While the Boomerang Nebula achieves its chill by expanding rapidly, like cosmic refrigerant spraying from a can, human-made cold relies on trapping atoms with lasers and magnetic fields. Picture this: researchers zap a cloud of rubidium or sodium atoms with precisely tuned lasers, effectively creating a light cage that slows their movement. Then they use evaporative cooling, letting the most energetic atoms escape like steam from a kettle, leaving only the slowest, coldest ones behind. The result: a blob of matter so cold that quantum effects, normally invisible, take center stage. Atoms lose their individual identities and merge into a single quantum wave, a superfluid with zero viscosity, where stirring it creates vortices that spin forever without slowing down. Why go to such extremes? These ultra-cold experiments are windows into quantum mechanics, revealing how particles behave at scales we can't yet observe in distant space. The condensates mimic conditions near black holes or the early universe's soup of particles, helping physicists test theories about dark matter or quantum gravity. It's a paradox. To understand the cosmos' hottest, most violent events, we must first master the art of freezing things to nearly nothing. Meanwhile, the Boomerang Nebula's cold is almost accidental, a byproduct of a dying star's last gasp. As its central star sheds material at 300,000 miles per hour, the gas expands so fast it can't absorb heat from the cosmic microwave background, the faint glow left over from the Big Bang. It's nature's version of cooling by sweating, and it held the title for coldest natural place until lab techs outdid it. So which is more impressive? The nebula's effortless galaxy-scale chill, or humanity's microscopic mastery of quantum cold? Both are marvels, one born from stellar death, the other from human curiosity. Together, they prove that temperature isn't just about numbers. It's a story of how matter behaves when pushed to its limits, whether by the laws of physics or the ingenuity of scientists armed with lasers and sheer stubbornness. Imagine a planet where the ground isn't made of rock or ice, but diamond, a glittering, ultra-dense world where the very soil could crush a diamond anvil into dust. Meet 55 Cancri E, an exoplanet 40 light-years away that astronomers suspect is literally packed with carbon crystals. This isn't science fiction. It's a real celestial oddity, a world where pressure and heat have likely turned much of the planet's interior into a diamond matrix. Picture Earth's crust, but swap the silicate minerals for a labyrinth of gemstones stretching hundreds of miles deep, with a core that might resemble a cosmic jeweler's workshop gone rogue. But here's the twist: this diamond paradise is anything but hospitable. 55 Cancri E orbits so close to its star that a single year lasts just 18 hours, and surface temperatures soar to 4,000 degrees Fahrenheit, hot enough to vaporize tungsten. The dayside is probably a molten wasteland of bubbling carbon, with supersonic winds howling across the surface. Some models even suggest that under such extreme pressure and heat, carbon atoms in the atmosphere could crystallize into diamond rain, only to melt again before reaching the surface. It's like a perpetual gemstone thunderstorm where the sky periodically dumps liquid diamond droplets into a seething carbon ocean below. How did this planetary jewel form? Most rocky planets like Earth are oxygen and silicon rich, but 55 Cancri E's star has an unusually high carbon-to-oxygen ratio. Think of it as stellar alchemy. When the planet coalesced from its primordial disk, it gobbled up carbon like a cosmic vacuum cleaner, stuffing itself with enough raw material to forge diamonds on a planetary scale. Over time, the crushing pressures deep inside likely compressed that carbon into crystalline structures, creating a mantle that could be 30% diamond by volume. That's trillions of carats worth, though mining it would require surviving conditions that make Venus look like a ski resort. The real kicker, 55 Cancri E might not be alone. Scientists speculate that carbon-rich worlds could be common around stars with similar compositions, meaning the galaxy could be littered with diamond planets, each one a monument to the universe's ability to turn chemistry into spectacle. Yet for all its allure, this world is a cautionary tale about first impressions. A diamond planet sounds luxurious until you realize it's a broiling, high-pressure hellscape where the very ground beneath your feet would be your doom. It's the universe's ultimate irony, a treasure chest no one can open, a gemstone forged in conditions too brutal to admire. So while we might never walk on 55 Cancri E's glittering surface, its existence reminds us that the cosmos loves a good plot twist, especially one that sparkles. The Milky Way has a secret flavor, and it's not what you'd expect. Deep in the heart of our galaxy, floating within a massive molecular cloud called Sagittarius B2, astronomers have detected a whiff of ethyl formate, the very same molecule that gives raspberries their sweet, tangy aroma and lends rum its distinctive fruity kick. That's right, if you could take a cosmic deep breath in the middle of the galaxy, it might smell like a distillery's backroom mixed with a berry patch. This bizarre discovery came from radio telescopes tuned to the frequencies of complex molecules drifting between the stars. Sagittarius B2, a swirling nursery of gas and dust near the galactic center, is like a sprawling interstellar kitchen, packed with chemical ingredients that shouldn't exist in the vacuum of space. Alongside ethyl formate, scientists found vinyl alcohol, which smells like cheap wine, and even glycolaldehyde, a simple sugar. Together, they create a scent profile that's less void of space and more interstellar cocktail hour. How does boozy, berry-scented gas survive in the cosmos? The answer lies in the shielding embrace of dust clouds. These thick molecular regions act like cosmic refrigerators, preventing harsh ultraviolet radiation from breaking apart delicate organic molecules. Over millions of years, atoms bump into each other and stick, forming increasingly complex compounds, some of which just happen to smell like dessert. Before you book a one-way ticket to this galactic tiki bar, there's a catch. Sagittarius B2 isn't exactly breathable air. It's a diffuse haze where these molecules are spread thinner than a single grain of sand in a football stadium. And the cloud's other residents, like hydrogen sulfide, which reeks of rotten eggs, would ruin the party fast, but the sheer absurdity remains. The same chemistry that flavors your rum cake exists in the void, proof that the universe has a sense of humor. What's truly mind-bending is what this means for life's ingredients. Ethyl formate isn't just a quirky scent, it's a building block for more complex organic molecules. Finding it in space suggests that the raw materials for flavors, fragrances, and even life itself might be sprinkled liberally across the galaxy. So next time you sip rum or bite into a raspberry, remember, you're tasting a hint of the Milky Way's hidden recipe, a cosmic kitchen where molecules mix in ways we're only beginning to sniff out. Solar flares don't just knock satellites out of commission sometimes, they shock them back to life like some kind of cosmic defibrillator. Take LES-1, a communications satellite launched by the US Air Force in 1965. After failing in orbit and going silent, engineers assumed it was just another piece of space junk, until 46 years later when amateur radio operators suddenly picked up its ghostly signal. The satellite, long declared dead, was somehow transmitting again, its electronics mysteriously rebooted by decades of solar radiation bombarding its circuits. Scientists call this phenomenon zombie satellite syndrome, and it's as eerie as it sounds. Here's how it works when a satellite dies. It's usually because a power surge or component failure knocks it offline, but the hardware itself might still be intact. Over time, charged particles from solar flares and cosmic radiation build up in the satellite's materials, creating tiny electrical imbalances. Eventually, a particularly strong solar storm can jolt these dormant systems, discharging the built-up static and effectively jump-starting the satellite's electronics. It's like leaving a calculator in a drawer for years, then pulling it out to find the battery somehow has enough juice to flicker back on. LES-1 isn't alone. In 2012, the British satellite UCube-1 unexpectedly woke up after months of silence. Its scrambled transmissions hinting at radiation-induced chaos in its systems. Even NASA image satellite, which vanished in 2005, suddenly started broadcasting in 2018, 13 years after its last contact before going silent again. These aren't coincidences, they're proof that space weather doesn't just disrupt satellites, it can reanimate them. The real twist: zombie satellites are often unstable. Radiation doesn't neatly repair circuits, it scrambles them. LES-1's signal, for instance, wavered in and out like a flickering light bulb, its carrier wave distorted as if the satellite itself was confused. Some resurrected birds start broadcasting nonsense data. their guidance systems so mangled they can't even orient themselves properly. It's less a second life and more a temporary glitch, a brief electronic gasp before the void reclaims them. This phenomenon poses a unique headache for space agencies. A zombie satellite could suddenly interfere with active missions, hogging radio frequencies or even colliding with operational spacecraft because its navigation systems are fried. And with solar activity ramping up toward the peak of its 11-year cycle, the risk of more undead satellites waking up only grows. Scientists now monitor old orbital relics extra closely, knowing any one of them could lurch back to life with the next solar sneeze. So the next time you hear about a solar flare, remember, it's not just a light show. It's a cosmic wild card capable of turning forgotten tech into temporary ghosts, silent one moment, chattering the next, as if the universe itself can't resist hitting the reset button on the dead. Mars doesn't just shake, it hums. When NASA in Sightlander planted its seismometer on the rusty plains of Elysium Planitia, scientists expected to detect the occasional tremor. What they didn't anticipate was how eerily long those vibrations would linger. On Earth, earthquakes typically last seconds to minutes, their energy dissipating quickly through our planet's fractured, waterlogged crust. But on Mars, seismic waves from Mars quarks can echo for over an hour, ringing through the planet like a gong struck in a silent cathedral. The reason lies in Mars' dead, dry interior. Without active plate tectonics to recycle its crust, the red planet's outer shell is a single, unbroken lid of rock, cold, rigid, and incredibly efficient at transmitting vibrations. Earthquakes here are muffled by oceans, molten magma, and shifting continental plates, but on Mars, seismic waves travel unimpeded for hundreds of miles, bouncing off subsurface layers and fault lines with barely any loss of energy. It's the difference between dropping a pebble in a pond Earth and tossing one into an empty swimming pool Mars. The ripples just keep going. In CITES, data revealed something even stranger. Mars quarks come in two flavors. The most common are shallow, brittle cracks caused by the planet's crust slowly shrinking as it cools, like a deflating balloon left in the freezer. These rumbles rarely exceed magnitude 3.5, barely enough to rattle dishes on a shelf, but their waves still reverberate for ages. Then there are the deep quakes originating hundreds of miles below the surface, where the mantle's sluggish convection might still be tweaking the planet's spine. These are rarer but pack more punch, and their low-frequency signals can take nearly 2 hours to fade completely. The quietness of Mars amplifies the effect. Without bustling cities, crashing waves, or even much wind, the planet's background noise is almost non-existent. In CITES seismometer, shielded from the elements by a domed wind and thermal shield, picks up vibrations so subtle they'd be drowned out on Earth by a passing truck. This silence lets scientists detect quakes as faint as a single atom's width of ground motion and trace their paths with astonishing precision. Some waves even reveal hidden layers of sediment, ancient lava flows, or pockets of underground water ice, painting a sonogram of the planet's guts. What's haunting is how these quakes sound when sped up into audible range. Processed by seismologists, the data becomes a chorus of creaks and pops, like an old house settling in the dead of night, except this house is a frozen world that's been cooling for billions of years. Each tremor is a whisper from Mars' distant past, hinting at when it might have had a molten core, a magnetic field, and maybe even the warmth to host life. So while Mars lacks the tectonic drama of Earth, its quakes tell a different story, one of a planet slowly turning inward, its seismic sighs lasting so long they blur the line between catastrophe and lullaby. Every vibration is a clue not just to what Mars is now, but to what it used to be and why it fell so quiet. The Moon isn't just a silent, lifeless rock. It's a world that shudders and groans under forces both seen and unseen. Scientists call these lunar tremors moonquakes, and they come in flavors far stranger than anything we experience on Earth. Some are gentle murmurs, barely detectable. Others are powerful enough to last 10 minutes or more, their vibrations echoing through the moon's brittle crust like a bell struck by a phantom hammer. What's causing all this shaking? For starters, tidal forces. Earth's gravity doesn't just pull on the moon's oceans because it has none. It tugs at the solid rock itself, flexing the entire lunar surface like a stress ball in an invisible fist. These deep moonquakes originate hundreds of miles below the surface, where the strain of Earth's relentless grip triggers fractures in the moon's rigid mantle. Then there are the thermal quakes caused by the moon's extreme temperature swings. As sunlight returns after 2 weeks of frigid darkness, the surface rock expands rapidly, creating sharp cracks that ripple through the regolith like ice settling on a frozen lake. But the most dramatic moonquakes come from meteor impacts. Unlike Earth, the moon has no atmosphere to burn up incoming space rocks, so even small asteroids slam into the surface at full force, sending seismic waves racing through the ground. Apollo astronauts left seismometers behind during their missions, and those instruments recorded some truly bizarre events. One meteor strike in 1972 rattled the moon for over half an hour, its vibrations bouncing between subsurface layers like a ping-pong ball in a cavern. The real surprise, the moon's seismic waves behave nothing like Earth's. Without water or sediment to dampen the vibrations, they travel farther and last longer. Some quakes produce low-frequency rumbles that take ages to fade, while others send sharp, high-pitched jolts through the crust. It's as if the moon's entire structure is one giant tuning fork, resonating with every cosmic nudge. This isn't just academic curiosity, it's a vital puzzle for future lunar colonists. Imagine building a moon base only to have its walls rattled by quakes that never seem to end. Engineers are already designing flexible structures and shock-absorbing foundations to withstand these tremors. Some proposals even suggest anchoring habitats to bedrock, bypassing the loose, quake-prone regolith entirely. So while the moon might look still from our vantage point, it's anything but quiet underground. Every shudder, every crack is a reminder that even dead worlds have their own kind of heartbeat, one that future explorers will need to listen to carefully if they want to stay standing. Astronauts returning from long missions often bring back an unexpected souvenir, feet as soft as a newborn baby's. That's right, space turns your skin into something resembling lizard scales, shedding calluses like a snake molting its skin. Here's why. On Earth, gravity and constant friction from walking keep our feet rough and toughened. But in microgravity, there's no pressure, no rubbing against shoes or floors. Without that daily wear and tear, the outer layers of skin stop thickening, and astronauts' feet become startlingly smooth. Some crew members have even joked they need to relearn how to walk without wincing when they return home, their souls suddenly sensitive to textures they hadn't felt in months. But the real kicker, all that dead skin doesn't just vanish. In the confined, floating environment of the ISS, those flakes don't fall to the ground, they drift. Imagine tiny, invisible snowflakes of former calluses suspended in the air, only to be caught by the station's air filters or, worse, inhaled by unsuspecting crewmates. Astronaut Scott Kelly described the phenomenon with a mix of amusement and mild horror, recalling how flakes would occasionally glint in the sunlight like specks of floating glitter. It's one of those bizarre, unglamorous realities of spaceflight nobody warns you about. You're not just shedding skin cells, you're turning the cabin into a zero-G dandruff snow globe. The science behind this is surprisingly practical. Skin cells naturally slough off over time, but Earth's gravity ensures they drop away. In space, without that downward pull, the process gets creative. NASA even had to redesign exercise equipment on the ISS to account for this, adding grips and padding that wouldn't irritate suddenly delicate feet. There's also the hygiene factor. More frequent vacuuming and air scrubbing are a must unless you want your crewmates breathing in your epidermal confetti. Here's the twist: while astronauts' feet go soft, their hands often get rougher. Constant use of tools, grips, and gloves in space can leave hands calloused in weird new places, a reminder that microgravity doesn't erase labor. It just redistributes the wear and tear. It's a trade-off, baby soft soles, mechanics palms. So next time you complain about dry skin, picture an astronaut floating in a capsule, surrounded by their own microscopic skin cloud, scratching their head at how something as simple as gravity shapes the most mundane parts of being human. Turns out, space doesn't just change how you look, it changes what you're made of, one flake at a time. Deep in the cosmos, 12 billion light-years from Earth, floats a black hole so unimaginably massive that it hosts the largest reservoir of water ever discovered. A swirling, superheated cloud holding 140 times the water of all Earth's oceans combined. Wrapped around a voracious quasar named APM 08279 plus 5255, this vapor shroud spans hundreds of light-years, a cosmic sponge soaked with enough H2O to drown entire galaxies in liquid. And here's the kicker, it existed when the universe was barely 1.6 billion years old, a time when scientists thought such colossal water reserves were impossible. Quasars like this one are the universe's ultimate powerhouses, supermassive black holes devouring matter so fast they outshine entire galaxies. As gas and dust spiral into the abyss, friction heats them to millions of degrees, blasting out energy that can be seen across the cosmos. But this particular quasar did something unexpected. Its radiation excited the surrounding gas molecules, causing them to emit a specific frequency detectable by radio telescopes. When scientists analyzed those signals in 2011, they found the unmistakable fingerprint of water vapor, trillions of tons of it, suspended in space like steam over a kettle the size of a solar system. The discovery upended everything we thought we knew about water in the early universe. Conventional models suggested that heavy elements like oxygen necessary for water molecules should have been scarce so soon after the Big Bang. Stars needed time to forge oxygen in their cores and spew it into space via supernova, meaning vast water reserves weren't supposed to appear until much later. Yet this quasar's vapor cloud defies that timeline, implying that gargantuan reservoirs of water coalesced shockingly fast, likely in the turbulent nurseries around young, hyperactive black holes. How did water get there so quickly? One theory points to ultra-efficient cosmic recycling. Quasars don't just consume matter, they belch it back out in colossal jets. These outflows, rich with newly minted oxygen from short-lived massive stars, could have mixed with abundant hydrogen in the surrounding clouds, creating water molecules almost as fast as the universe could produce the ingredients. Another idea suggests that shockwaves from the quasar's radiation compressed nearby gas, accelerating chemical reactions that wouldn't occur under calmer conditions. Either way, the implications are staggering. Water, the elixir of life, might have been a cosmic inevitability rather than a rare accident. Yet for all its scale, this aquatic wonderland is anything but hospitable. The water here isn't liquid or even ice, it's a searing plasma, superheated by the quasar's fury to thousands of degrees, and it's not floating peacefully. The cloud churns in a maelstrom of radiation and gravitational tides, its molecules constantly torn apart and reassembled. This isn't a place you could drink from, it's a laboratory for extreme chemistry, where the universe stress tested its recipes for building blocks long before Earth existed. The real marvel, this record-breaking reservoir might not be unique. Other distant quasars show hints of similar water vapor halos, suggesting that the early cosmos was far wetter than we ever imagined. Every new detection peels back another layer of cosmic history, revealing a universe that didn't just wait for the right conditions to make water. It cooked up oceans in the unlikeliest of places, against timelines we're only beginning to untangle. So while APM 08279 plus 5255 holds the crown for now, it's probably just the first of many cosmic oases we'll find, rewriting the story of how water, and perhaps life got its start. Beneath Europa's frozen crust lies one of the most tantalizing secrets in our solar system, a global ocean, so vast it holds twice as much water as all Earth's seas combined. This isn't just any ocean, it's a swirling, salty abyss locked under miles of ice, warmed by Jupiter's relentless gravitational squeeze and possibly teeming with the ingredients for life. Scientists call it the Golden Moon for good reason. Its fractured, golden-brown ice shell, crisscrossed with reddish scars, hints at an alien waterworld just waiting to be explored. What makes Europa's ocean so special isn't just its volume, it's the way it interacts with the Moon's rocky core. On Earth, life clusters around hydrothermal vents, where mineral-rich water gushes from the seafloor, feeding entire ecosystems in perpetual darkness. Europa could have its own version, volcanic vents on the ocean floor, spewing chemistry into the water like an extraterrestrial cauldron. The Hubble Space Telescope has even spotted plumes of water vapor erupting from Europa's south pole, suggesting the ocean occasionally punches through its icy lid, offering free samples to any passing spacecraft. This isn't wild speculation. Galileo, NASA's 90s-era Jupiter probe, detected a weak magnetic field around Europa, something only possible if a conductive fluid like salt water exists beneath the surface. Then there's the Moon's peculiar surface geology, chaotic lenticulae, blobs of disrupted ice that might be melt zones where warm water wells up, and double ridges that resemble skyscraper-sized zippers in the ice, possibly formed by tides flexing the crust. Put it all together, and you've got a moon that behaves less like a frozen rock and more like a giant, sloshing snow globe with a liquid heart, the real game changer. Upcoming missions like Europa Clipper, set to launch in 2024, this nuclear-powered spacecraft won't land, but it'll skim just 16 miles above Europa's surface, mapping the ice thickness, analyzing plume chemistry, and even testing whether the ocean communicates with the surface through salty brines that percolate upward. Future missions might drop robotic submarines or cryobots to melt through the ice, deploying sensors into the alien water below. Imagine a probe tasting Europa's ocean for amino acids or spotting microbial life floating in the darkness, glowing like deep-sea creatures in Earth's abyss. Here's the mind-blowing part. Europa isn't alone. Saturn's moon Enceladus also has a subsurface ocean and sprays its contents into space, while Ganymede, Jupiter's largest moon, may harbor layers of liquid water sandwiched between ice. But Europa's ocean is special because of its sheer stability. It's likely existed for billions of years, giving life, if it's there, an eternity to evolve. Some astrobiologists think organisms in Europa's depths could resemble Earth's extremophiles, creatures thriving near volcanic vents without sunlight, fueled by chemistry alone. The implications are staggering. If life exists in Europa's shadows, it would prove that biology isn't a fluke of Earth. It's a cosmic inevitability, flickering wherever water, energy, and time intersect. This tiny moon, just one of Jupiter's 79 known satellites, could hold the answer to whether we're alone in the universe. And with every fractured ice ridge and spewing plume, Europa seems to be shouting the same message: come and look. The ocean is waiting. Venus doesn't just break the rules, it flips them upside down and sets them on fire. While most planets spin like tops as they orbit the Sun, Venus moves in slow motion, dragging out each rotation over 243 Earth days. That's longer than its entire year, which clocks in at just 225 days. Picture this: you could celebrate 2 birthdays on Venus before a single sunrise and sunset cycle completes. It's the solar system's ultimate time warp, where calendars and clocks lose all meaning. This backward rhythm isn't just a quirk, it's a cosmic anomaly with violent origins. Most astronomers agree Venus was likely knocked sideways by a cataclysmic collision billions of years ago. A smash-up so brutal it sent the planet spinning in reverse like a derailed merry-go-round. But gravity and friction didn't leave it alone afterward. The planet's thick, soupy atmosphere, 90 times denser than Earth's, acts like an anchor, dragging against the surface with winds that scream at 225 miles per hour. These aren't gentle breezes, they're hypercharged rivers of gas that whip around the planet every 4 days, a phenomenon called superrotation. Imagine a hurricane the size of a planet, spinning faster than the ground beneath it, and you've got Venus's atmospheric nightmare. The sheer weight of that atmosphere plays tug-of-war with the planet's rotation. Like a spoon stirring molasses, the turbulent air layers tug on Venus's crust, slowing its spin over eons. Some models suggest this atmospheric break could have even reversed the planet's original rotation, turning it into the cosmic oddball we see today. And here's the kicker: those winds aren't just fast, they're eerily consistent, circling the planet in a never-ending loop without the turbulence of Earth's jet streams. It's as if Venus's sky has a mind of its own, indifferent to the sluggish world below. Down on the surface, this sluggish rotation creates hellish extremes. The sun, when it finally rises, crawls across the sky for months, baking the rocks at 860 degrees Fahrenheit. Nights last just as long, with temperatures barely dropping because the thick atmosphere traps heat like a wool blanket. And since Venus rotates clockwise opposite most planets, the sun rises in the west and sets in the east, as if the universe flipped a switch on reality itself. Yet for all its violence, there's a strange beauty to Venus's contradictions. Its atmosphere, though deadly, glows with an ethereal yellow hue, and its high-altitude clouds reflect sunlight so brightly the planet outshines every star in the night sky. It's a world that refuses to conform, spinning backward, simmering under perpetual storms, and challenging every assumption we have about how planets should behave. Venus doesn't just march to the beat of its own drum, it rewrites the sheet music mid-song and dares the universe to keep up. So while we marvel at Mars' canyons or Jupiter's storms, Venus quietly defies logic, a shimmering enigma wrapped in acid clouds. Its twisted sense of time and motion remind us that even in the orderly dance of the solar system, outliers exist, worlds that took chaos and turned it into their own kind of rhythm. Human hearts weren't designed for space, something astronauts learn the hard way when their most vital organ starts reshaping itself like a balloon in zero gravity. After just a few weeks in orbit, the heart transforms from its usual tapered shape into something closer to a sphere, a bizarre adaptation that might sound harmless but throws off the finely tuned mechanics of blood flow. Without gravity pulling blood downward, fluids redistribute upward, tricking the heart into thinking it's overfilled. The organ responds by weakening its muscle tone, shrinking in mass, and rounding out like an overinflated basketball, up to 10% more spherical, according to NASA ultrasounds. This isn't just a quirky change, it's a workload nightmare. A spherical heart pumps blood less efficiently than its Earth-shaped counterpart, forcing astronauts to exert more energy for basic tasks. Imagine trying to siphon water through a hose by squeezing a round sponge instead of a directional pump. You'd get flow, but it'd be sluggish and uneven. That's the challenge spacefarers face, especially on long missions where the heart's slow decline could lead to dizziness, fatigue, or even fainting upon return to gravity. Studies of International Space Station crews show some lose up to 20% of their heart's pumping capacity after 6 months aloft, a staggering drop equivalent to decades of aging. Countermeasures exist, but they're as peculiar as the problem itself. Astronauts strap into lower body negative pressure suits, essentially vacuum-sealed pants that artificially pull blood back toward their legs, mimicking gravity's effects. These contraptions look like high-tech waders crossed with sci-fi medical gear, using suction to stress the cardiovascular system and keep the heart from growing lazy. Then there's the exercise regime, 2-hour daily marathons on treadmills and resistance machines, all to trick the heart into working harder than microgravity demands. Even with these efforts, some muscle atrophy is inevitable, like trying to bench press in a world where the barbell weighs nothing. The real concern, Mars. A round-trip mission could last 3 years, giving hearts ample time to weaken in ways we don't fully understand. Scientists are racing to develop better solutions, from vibrating plates that stimulate circulation to drug cocktails that slow muscle loss. Some even propose artificial gravity stations, spinning modules where centrifugal force substitutes for Earth's pull. What's fascinating is how this echoes broader truths about human biology. Our bodies aren't just adapted to Earth, they're sculpted by it, down to the very shape of our organs. Space reveals how fragile that balance is, turning the heart's elegant asymmetry into a liability beyond our atmosphere. Every beat in zero gravity is a reminder we're not just visitors to the cosmos, we're prisoners of gravity, and our hearts know it. The sun doesn't just rise and set, it flips its entire magnetic field like a cosmic switch every 11 years, turning itself inside out without warning. This isn't some quiet, invisible shift. It's a full-scale polar reversal, where the sun's north and south magnetic poles swap places in a process that sends shockwaves through the solar system. Imagine Earth's compasses suddenly pointing south instead of north, then multiply that chaos by a factor of 1,000,000, and you've got the solar cycle's most dramatic act. Right now, we're barreling toward the next reversal, expected between 2024 and 2025. As the sun approaches this milestone, its magnetic field grows increasingly tangled, like a ball of yarn twisted too tightly. Sunspots, those dark, cooler patches on the solar surface, multiply like freckles, clustering near the equator as the star's internal dynamo reshuffles itself. Then, at the peak of this upheaval, the poles officially flip, and the sun's magnetic influence stretches outward like an invisible spiderweb, realigning the entire heliosphere. What does this mean for us? For starters, auroras could light up skies at lower latitudes than usual, painting nightscapes with surreal greens and purples where they're rarely seen. The last polar flip in 2013 triggered dazzling displays as far south as Colorado and the UK, as solar winds collided with Earth's magnetosphere in rippling waves. But the real show happens in space itself. Solar flares and coronal mass ejections become more frequent and intense leading up to the reversal, hurling radiation and charged particles that can disrupt satellites, radio signals, and even power grids. In 1989, a geomagnetic storm during this volatile phase knocked out Quebec's electricity for 9 hours, a preview of what can happen when the sun gets moody. Yet for all its drama, the flip isn't the doomsday event some conspiracy theorists claim. Earth's own magnetic field acts as a buffer, deflecting the worst of the solar tantrums. And counterintuitively, the reversal might actually help shield us from deep space threats. During the transition, the sun's twisted magnetic field forms a rippled current sheet that deflects galactic cosmic rays, high-energy particles from supernovas and black holes, like a cosmic umbrella. Astronauts on the ISS and future Mars travelers could benefit from this natural shielding, as cosmic ray exposure drops by up to 20% during solar maximum. The most fascinating part, we're only beginning to understand why this happens. The sun's magnetic field is generated by the movement of plasma deep in its interior, a process called the solar dynamo. As this churning plasma twists and stretches, it amplifies magnetic energy until the system can't hold its shape anymore, like a rubber band stretched too far. The poles snap, resetting the cycle. It's a self-correcting mechanism, a stellar heartbeat that's pulsed predictably for millennia. Ancient tree rings and ice cores show evidence of these cycles stretching back 11,000 years, proving this isn't a fluke, it's the sun's natural rhythm. So while the reversal might sound apocalyptic, it's really just routine maintenance for a star that refuses to sit still. The same magnetic mayhem that creates solar storms also fuels the solar wind, which in turn carves out a protective bubble around our solar system, fending off interstellar radiation. Without this cycle, the heliosphere would weaken, leaving us exposed to the void. In the grand scheme, the sun's flip is less a crisis and more a reminder of how deeply we're tied to our star's whims. Its magnetic tantrums shape our technology, our skies, even our exploration plans. And when those poles finally switch places, it won't be the end of the world, just another chapter in the sun's endless dynamic story. Buried within the Milky Way's shimmering spiral arms lies the ghost of an ancient massacre. Gaia Enceladus, a dwarf galaxy our cosmic neighborhood devoured 10 billion years ago. This wasn't some gentle merging of stars, it was a violent feast, a celestial collision that reshaped our galaxy's destiny. Today, the remnants of this long-dead galaxy still haunt us, their stars scattered like cosmic confetti across the Milky Way's halo, invisible to the naked eye but unmistakable to astronomers armed with modern surveys. These aren't just random stars, they're fossils of a forgotten apocalypse, whispering secrets about how galaxies grow by consuming their neighbors. The discovery of Gaia Enceladus reads like a forensic detective story. For decades, astronomers noticed something odd about a subset of stars in our galaxy's outer reaches. These stars moved differently against the Milky Way's rotational current, and their chemical makeup was all wrong, richer in heavy elements like iron than native Milky Way stars. Then, in 2018, the European Space Agency's Gaia mission delivered a bombshell. Precise 3D maps of over 1 billion stars revealed a distinct population orbiting backward, their paths tracing the gravitational scars of an ancient merger. Connecting the dots, scientists realized these stars were the survivors of Gaia Enceladus, a dwarf galaxy roughly 1/5 the Milky Way's mass that met its end in a slow-motion crash lasting billions of years. What's eerie is how thoroughly the Milky Way digested its prey. Gaia Enceladus's core was torn apart, its stars flung into chaotic orbits that now cross our galaxy like celestial strays. Yet some clues remain pristine. The dwarf's original stars were older and metal-poor, suggesting it formed in the early universe before supernova had seeded space with heavier elements. By contrast, the Milky Way stars from that era are far rarer, having been diluted by later generations of star formation. This makes Gaia Enceladus's remnants a time capsule, preserving a snapshot of galactic chemistry from an era when the universe was still in its wild youth. The aftermath of this collision wasn't just destructive, it was creative. The merger likely triggered a burst of star formation in the Milky Way, flooding our galaxy with new suns as incoming gas and dust compressed under gravitational forces. Some models even suggest the Milky Way's iconic spiral arms might owe their structure to this ancient upheaval, as the violence of the collision sent ripples through our galaxy's disk. It's a cosmic irony. The death of one galaxy helped shape the beauty of another. But Gaia Enceladus isn't alone in the Milky Way's graveyard. Other dwarf galaxies like Sagittarius and the Sequoia have also been absorbed over billions of years, their stars assimilated into our galactic fabric. This pattern reveals a universal truth. Galaxies are not static islands but dynamic ecosystems, growing through cannibalism and mergers. The Milky Way's serene appearance today belies its violent past and future. In 4 billion years, when the Andromeda Galaxy collides with us, a similar fate awaits, two spirals merging into one, their stars reshuffled like cards in a deck, birthing a new galaxy whose history will be written in the ashes of giants. Yet Gaia Enceladus's legacy lingers. Its stars, now unrecognizable to the untrained eye, continue to orbit, their motions encoding the memory of a cataclysm older than Earth itself. For astronomers, these stellar refugees are more than just artifacts, they're proof that even the grandest structures in the universe are built on foundations of chaos, their histories etched in light that outlasts empires. So the next time you gaze at the Milky Way, remember, you're not just seeing stars, you're witnessing the aftermath of a 10-billion-year-old crime scene where our galaxy's hunger forged the heavens we call home. Space doesn't just change astronauts' muscles and bones, it rewrites their very DNA. Take NASA, a groundbreaking twin study where Scott Kelly spent nearly a year aboard the International Space Station while his identical twin, Mark, remained on Earth. Scientists expected some physical differences, but the genetic revelation stunned everyone. Scott's telomeres, the protective caps at the ends of chromosomes that shorten as we age, did the unthinkable. They grew longer in space, as if his cells were hitting the rewind button on aging. It was like watching a biological magic trick, one that defied decades of research linking stress and radiation to accelerated cellular decay. Then came the twist. Within months of Scott's return to Earth, those elongated telomeres abruptly shrank back to near pre-flight lengths, some even shorter than Mark's. It was a roller coaster of cellular drama, hinting at how microgravity and cosmic radiation wage a tug of war with human biology. One theory suggests that the extreme environment of space triggers survival mechanisms in cells, temporarily boosting repair processes to cope with the onslaught of stressors. But like an overworked engine, those systems can't sustain themselves forever. The toll of spaceflight isn't just skin deep, it's etched into the blueprint of life itself. The real villain in this story, cosmic radiation. Earth's magnetic field shields us from the worst of it, but astronauts in orbit are bombarded by high-energy particles from solar flares and distant supernovas. These subatomic bullets slice through DNA like microscopic shrapnel, causing damage that cells struggle to repair. Scott's blood samples revealed cosmic rays had scrambled parts of his genetic code, creating mutations that lingered even after his return. Most were harmless, but some affected genes tied to immune function and bone formation, a warning sign for future Mars travelers facing years of deep space exposure without Earth's protective magnetosphere. Yet hope isn't lost. Scientists are already testing futuristic countermeasures, from gene-editing therapies like CRISPR to radioprotective drugs that could shield DNA from radiation. Some experiments involve injecting astronauts with engineered stem cells to repair damaged tissues mid-mission, while others explore wearable magnetic fields that mimic Earth's defenses. There's even talk of modifying spacecraft hulls with water-rich polymers, literally lining walls with radiation-absorbing H2O. The twins' study wasn't just about Scott and Mark, it was a wake-up call. If we're serious about Mars, we can't just engineer better rockets, we'll need to engineer ourselves. Whether through advanced medicine, synthetic biology, or some yet undiscovered breakthrough, the future of space travel might depend less on how far we can go and more on how well we can adapt. After all, the cosmos isn't just a place to visit. It's a mirror reflecting back the incredible fragility and resilience of being human. From diamond planets where the very ground beneath your feet would crush you, to zombie satellites jolted back to life by solar flares, space doesn't just defy our expectations, it revels in flipping them upside down. Who could forget the hexagonal storm on Saturn, a swirling geometric masterpiece big enough to swallow Earth whole, or the moon's bizarre gunpowder scent that clung to astronauts like cosmic campfire smoke? And let's not overlook the star so dense a single teaspoon weighs a mountain, or the galaxy that smells like raspberries and rum. Every corner of the cosmos seems to whisper, "You think you've got me figured out." Think again. What makes these discoveries so thrilling isn't just their weirdness, it's the way they humble us. For every law of physics we think is unbreakable, space serves up an exception. Planets spin backward, black holes hum like bass guitars, tears float away like rebellious jellyfish. Even the emptiness of space is a misnomer, packed with water clouds the size of oceans and magnetic flip-flops that rewrite the rules every 11 years. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and that's what keeps us staring skyward, hungry for the next revelation. So now it's your turn. Which of these cosmic oddities blew your mind the most? Was it the astronaut who grew 2 inches taller in space? or the Martian sunset that glows sapphire blue. Drop your favorites in the comments, or better yet, tell us what we missed. The universe is vast, and for every fact we've uncovered, there are a million more waiting to astonish us. And if you're craving more deep dives into space's greatest hits and mysteries, hit that subscribe button. The cosmos never stops surprising us, and neither will we. Until next time, keep looking up. The stars are just getting started.